This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, your professor for this University of Texas at Austin course, and we're at lecture 55. We're continuing on our discussion of lithography, and here we'll talk about line width control in general. So what is line width control? First of all, why is it important? The answer of why we care about line width, or as we often say in this business, the critical dimension, or CD. Dimension, of course, is the same as line width. We call it a critical dimension whenever we care about it. And there are plenty of dimensions we don't care that much about on the chip, and we just never measure them or worry about them. So anything we measure or pay attention to is going to be a critical dimension, or a CD. So why do we care about CDs? Well, the answer depends on what we're doing. What is it we're making? Different process layers, contact holes, silicon trench isolation, active area definitions, etc. all have different requirements because of the different functions of the features that we're building. But for any layer, our ability to construct the complex shapes that make our devices includes two pieces. One, CD control, the ability to control the width of the feature, but then there's also the overlay capability, which is the positioning of the pattern relative to the other patterns already on the wafer. Both of these things couple together, and they determine how closely we can pack things together. These are expressed in something called design rules, and our ability to pack features more closely together allows us to shrink the size of the chip, fit more chips on a wafer, and lower the cost of manufacturing that chip. And that's really what it's all about. A classic example of where we often talk about the importance of line width control is the gate. The gate of our CMOS or MOS transistor is very critical to the performance of that transistor. In particular, the gate switching time is proportional to the gate length. And the gate length is how wide the feature is, the size of the feature of the CD. We call it the gate length. And wider gates take longer to switch on and off, pretty much in direct proportion. So when we think about errors in the gate CD, we can relate them to these switching times. Let's take a look. Here is a frequency distribution of gate CDs that one might find on a wafer or across. Let's say it's across one chip. Of course, there might be thousands, millions, or billions, more typically today, of these gates and gate dimensions that we have to worry about. So if we were to measure a whole bunch of them and put them in a frequency plot, we might find a Gaussian-like shape like this. And maybe we worry about the center and how it matches the design or the target CD, but we also worry about the spread. So we want to control the center, we want to control the spread, and it affects performance in three different ways. First of all, the smallest transistor limits the reliability. So as we make the transistors too small, what happens is we can't quite turn them off. We try to turn off the transistor, but it doesn't turn off, and so it leaks current. If we have too many transistors that leak too much current, the result is excessive power consumption, and the device fails. So that's what happens if our CDs get too small. If our CDs get too big, then they are too slow. If they're too slow, especially we have a critical path, and so a path of one transistor after another that the signal has to propagate through, and the largest transistor in that critical path limits the speed that we can run the device. So if we have these big slow transistors, the device runs more slowly, and we suffer from something called bin sort. That is, after we make a whole bunch of chips, we might test them, and some of them can only run at slow speeds, and some can run at faster speeds, and we sell the faster ones for more money than the slower ones. So for nominally the same chip, we'll make less money if there are too many large transistors that slow down the chip speed. But this spread of these CDs also affects how fast we can run the clock. And this is something called skew, timing variations. If I have a signal propagating through a bunch of small transistors, it moves very quickly. If I have another signal propagating through some larger transistors, it moves more slowly to get there, and then they don't arrive where they need to be at the same time. You can get an error. That's called clock skew, and the range of feature sizes on the wafer affects this skew, and also ultimately the fastest clock speed we can run. So if we can tighten up this distribution, we can get better performance of our chips and sell them for more money. So let's look at what it takes to control the feature size in a lithographic process. First, it's very, very useful to think about errors in this total differential. You might recall from calculus what the total differential is. We say some delta variable, excuse me, delta CD is here. And what is that equal to? It's equal to actually a lot of things. Higher order terms, but if we think of small errors, then we can approximate the total delta CD as being delta CD per delta variable times delta variable. In other words, we can think about what affects CD control as two pieces. One is the magnitude of a process error. Right? Suppose this is the temperature of my hot plate. So delta T would be the variation of temperature across the hot plate. Then we have, that's the magnitude of the process error. Then we have the response of our process to that error, which is called the process latitude. This is the derivative dCd d variable. In the case of temperature, it's what's the sensitivity of the critical dimension to a change in temperature. So how do we reduce line width errors? How do we make delta CD smaller? Well, we have two ways. One is we can design processes that naturally have a low sensitivity to process variation. That is, a large process latitude. And we can work on reducing all the process errors that might occur. And a combination of both of these things is what gives us the best line width control. So these two things are quite separate, quite different. One of them, dCd d variable, this is about designing the process. It's about picking the right materials, the right equipment, designing the process so that it minimizes this derivative. Delta V, the magnitude of the process error, is about controlling the process, looking for all the ways in which we can improve, say, the temperature control of our hot plate, or how it varies across the hot plate. So very different tasks, and we do both of these things in lithography. Let's take an example. Line width varies with exposure dose. If I have a positive resist, the more I expose the resist, the more chemical change occurs that increases the solubility of the resist. So if I think about a line feature, the line being the region that's unexposed and the spaces on either side of the line are exposed, when I increase the exposure dose, I make the resist in the space regions even more soluble, and the width of that line shrinks. So here would be a plot of line width versus exposure dose for a positive resist. If I were to plot the space width versus exposure dose, it would have a function that went in the opposite direction. So the space width would get bigger with exposure dose for a positive resist. But here we show a line width. It's not a straight line, but over a small region near the nominal, so here's, suppose my nominal CD is a half a micron, my nominal exposure energy is 150 millijoules per square centimeter. This is an I-line case. And around this region, around this center point, it kind of looks like a straight line, and so my linearization of the problem will probably work well. We often define something called the exposure latitude, since it is typical to spec our feature sizes as requiring plus and minus 10% control. That is 3 sigma specifications of plus and minus 10%. I can go to my CD plus 10% here, read off the exposure dose that produces that, the CD minus 10%, read off the exposure dose that determines that. This range of exposure doses divided by the nominal dose is my exposure latitude. And if I wanted to improve CD control, I could try to improve the exposure latitude, or I could try to reduce the sources of exposure error in my process. But you have to be careful. Not every process variable is linear. We've looked at swing curves. Swing curves have sinusoidal variations. Often we try to pick a thickness at the minimum of the swing curve, in which case the process variation is about quadratic. It's not linear. So using the linear approximation in that case would be of no value. Another variable that produces a quadratic error in feature size is focus. When I go out of focus, plus focus errors and minus focus errors are just about the same, produce just about the same result, and there's a minimum at best focus. So if I look at line width versus focus, for example, here, it's quadratic, approximately quadratic. These, by the way, are different exposure doses. So focus and exposure are coupled in their response, in their ability to affect resist line width. At low exposure doses, going out of focus makes the line width bigger. At high exposure doses, going out of focus makes the line width smaller. So we can't use this linearization of our delta CD for all cases, but for some cases, in particular exposure, it works well. When we think about the errors in CDs, we often try to figure out what caused them. Right? So we see some result. There's a variation in the line width, and we want to dive down and say what's causing that variation and what can we do to improve it. Well, there's several different approaches that we take to analyzing CDs. One approach is to look for temporal variations. How does the CD vary with time? Here we use trend charts, which we saw in a previous lecture on statistical process control. We watch the variable with time and look for violations of the process control rules, the Western Electric rules, trends that might indicate something that has changed. We also look for spatial variations, and I'll talk more about that in the next few slides. Spatial variations would be variations that occur from wafer to wafer, and things that occur from lot to lot. But also, and more importantly, across wafer variations. We might find a systematic radial variation where the CDs in the middle of the wafer are different than the CDs on the outside. This might be due to an etch variation, for example, etching variation across the wafer in the etch chamber. We also worry about across field variations. Remember, a field is one region that is exposed in a single scan on a step and scan system, and we have a slit, and so we have a scan direction and a slit direction, and they're very different because we only scan in one direction, so any errors in the scanning only affect that direction, and the slit is much longer than it is wide, so in the slit direction we can have more variation caused by the optics of the imaging tool. These are what we look for here is systematic variations, but there's also just plain old random variations, and we need to characterize the magnitude of the random variations as well. Given that, there's two basic ways that we analyze errors. I'm speaking, of course, about semiconductor manufacturing here, but the approach that I'm taking, in fact, applies to virtually any manufacturing you could possibly think of. We often analyze errors in the results in a top-down way and in a bottoms-up way. What do I mean? Top-down means I look at the final result. I've printed the wafer, it's all done, and now I analyze those results. I do statistical analysis and look for systematic and random components within that final result. That's called top-down analysis. I start with the answer and try to work backwards. Bottoms-up analysis is the sources of variation. Instead of looking at the final answer, I look at the inputs to the process and try to understand where variations in the inputs come from. I measure the temperature variation across a hot plate. I measure the etch rate variation within a chamber. I measure the deposition rate variation in a spin coater or in a CVD deposition furnace. And I look for the sources of variation, the variations in the inputs. In terms of lithography, I might look at variation of the intensity of light across the slit. Maybe I don't get exactly the same intensity of light at one corner of the slit compared to the other. That would be a bottoms-up source of variation. Ideally, we do both bottoms-up and top-down analysis, and hopefully they match in the middle and help us explain the whole thing. Let's look at this top-down analysis in a little bit more detail. You've probably seen or thought about this kind of breakdown many times. We say a measurement. Say I pick a wafer and I measure it, and I measure the CD at various XY coordinates across the wafer. That's my measurement. What's the measurement consist of? It is the nominal value of the CD, the target, the thing I'm trying to achieve, plus any systematic errors that have occurred in the printing of that wafer, and random errors. So we say the error, which is the difference between what I got and what I wanted, has a systematic and random component. Well, that's not too shocking, not too revolutionary. But when I write it out like this, it will allow me to do the next step quite easily. What I'm going to do is not just measure one wafer at these exact XY coordinates and obtain this measurement result, but I'll measure a whole bunch of wafers. I'll measure n wafers. What am I going to do? Well, I'm going to average all of those wafers together and create a composite wafer. So if I take all the measurements and I average them together, that's the sum of all the measurements divided by n. Very simple, average. Then when I subtract off the target CD, what I have left is called the composite CD error. Composite meaning I've combined the n wafers together into one effective wafer. I've averaged them all together and subtracted off the CD. Okay, well, let's plug in our formula here. The measurement minus CD0 is the systematic error plus the random error. Right? And then I'll average them all together. What happens when I average all the systematic errors together? Well, by definition, systematic errors are just systematic errors. They're always the same. So the average is the same as the systematic error on any one wafer. Right? So when I average them, I simply get the systematic errors. But when I average the errors, the random errors, what I will get is approximately 0. I mean, after all, they're random, and random errors have, by definition, a 0 mean. Otherwise, it's a systematic error, and that would be included in the systematic wafer signature. So if I can increase n large enough, all of the random errors average away, average to 0, and my composite CD error at each wafer location becomes the systematic signature. Well, technically that's only true if I can measure an infinite number of wafers. When I measure a finite number of wafers, this random error will not average out to exactly 0. But I know how far away it's likely to be. So by determining the standard deviation of the residual of each measurement, that is, I can determine the random errors, I can estimate the standard deviation of the total random errors by the standard deviation of my sample. As a result, I say that the systematic errors equals the value I get when I do my composite CD errors, my average of the CD errors on all the wafers. But I know that this is not a perfect measurement. There's an uncertainty, and the uncertainty is the standard deviation of the random errors divided by the square root of n. So given my estimate of how big the random errors are, I can decide how many wafers n I need to measure in order to get a given amount of uncertainty in my measurement of the spatial signature. Then I can perform similar analysis for the composite field and the composite slit, and I can get these signatures, and I can try to understand them, and I can try to figure out what I can do to reduce them through some manipulation in my system. So let's review what we've learned about line-width control. Line-width control is governed by two factors: the magnitude of a process error and the response of the process to that error. Now, not every error is linear. Swing curves and focus effects are linear. And not every set of errors are independent. For example, focus and exposure dose work together to cause a variation in line-width. And so thinking of focus and dose independent of each other isn't very useful. Nonetheless, this linearization of the problem is quite useful, and thinking of an approach to improving line-width control as designing processes with good process latitude and then working on the process to minimize the sources of errors, very good thing. We know that CD control has concrete impacts on the performance of a device and on the yield. It depends on the specific layers, but we have some pretty good understanding in most fabs exactly how much CD control results in how much device performance or yield loss. And finally, CD errors are best characterized by using both a bottom-up sources of variation analysis and a top-down statistical spatial signature analysis approach. I focus more on the top-down approach here, but you can imagine that the bottoms-up approach would involve a lot of detailed work of understanding the specifics of all the equipment and materials in use. So, what have we learned in Lecture 55? As always, you should be able to quickly and easily answer these questions. How does transistor gate CD variation affect the device or the circuit? What two generic factors determine the resulting variation in CD? In particular, if we assume we can linearize the problem. Name two process variables that result in quadratic rather than linear CD response in lithography. And finally, explain the difference between a bottom-up and a top-down CD error analysis. Well, that's our lecture on CD control in general. Next time, we'll look specifically at exposure latitude, how exposure dose affects CD control, and relate that to lithographic quality. Till then.